So today we're talking about roots and exponents. And this guy here is the radical symbol. So sometimes you'll see that means square root. If you saw it something like this, that would be with a little 3 as the index there. That would be like cube root, and you might see fourth root, etc. So the first rule, and this property is not finished here, is when you take the nth root of a product here, we are allowed to, if that's multiplication, we are allowed to break up the square root or the cube root here. So we can say that's really the nth root of A times the nth root of B. And sometimes that's helpful. I mean, we wouldn't have to do that here, but we certainly could. Just want to show you what we could do here. Square root of 9 times 4 is the same thing as 36. So I could, using this property here, we could say that's really square root of 9 times the square root of 4. And that's going to come in handy sometimes, break things up into smaller parts. So that's really 3 times 2, which is, of course, 6. And we knew that the square root of 36 is 6, but I just wanted to show you how the property works here. So here's another one. You can have division inside of a radical. And so when that happens, you're allowed to break that up as well. So multiplication and division can both be broken up. So this would be the nth root of A over the nth root of B. And so here, this is handy now because I'm allowed to kind of say, okay, that's really square root of 9 divided by square root of 16 down below. So that's really 3/4. And then here we've got kind of an unusual situation. We've got a square root or some kind of root of another root. So we can put that together if we want to by saying the of A. But here in this index, it's hard to write it really small. It would be M times N. So I can't really write that small, but that's in the index right there. You're multiplying M and N. So in this case, by the way, when you see square root, it's really a second root in disguise. So just kind of know that it's a second root in disguise when you see that. So this is going to be, so in other words, there's kind of a little 2 right there whenever you see square root. So using the principle, so this would be using the property there, the 6th root of 64. Now you may say, I don't know what the 6th root of 64 is. That's okay. So off to the side, I'm going to kind of do a factor tree of 64. So say 2 times what? 32, 2 times 16, 2 times 8, 2 times 4, and finally 2 times 2. So I have 1, 2, 3, 4, 5, 6 2's that make up 64. So I could write this as the 6th root of 2 to the 6th power. Well, roots are kind of like the opposite of exponents. So if I have something like this, if I have something like I'm taking the 6th root of some number to the 6th power, it's going to come out really nicely. And that's just 2. Oh, in fact, there's a couple rules about this because there's a couple of kind of unique, and we're getting kind of picky here, but there's some unique things that happen when you do this kind of thing here, like the same root of the number. So when nth root matches the power, so when the index and the power match there, if n is odd, we treat it like this. So this is what, well, let's see what happens. So this would be, what would you think it would be? It would just be whatever this guy is will be it, right? So this will be -7. So this is equal to A. So that's exactly when it's odd, whenever it's an odd root. Like what I mean by odd root is when the index, the root, and the power are both odd, and they both match, then it's just A. You know, whatever this is, those just kind of undo each other. They counteract each other, and you're just left with -7. So nothing's unusual there, but there's something unusual that happens with even numbers. And this one's kind of a hard one to understand, but there's definitely just a little bit of a difference between the odd and the even. So let's look at this, and let's kind of do order of operations on this one. So I would probably do the step inside the parentheses first. So I would say, well, that's really the square root of 49, and I know the square root of 49 is 7. Well, that's interesting, because unlike this, where I came out with the same number that's inside the parentheses, -7 inside there, but it ended up with 7. That was maybe surprising to you. So that is correct here, but the formula, the property here, will be the absolute value of A. So this is a really unique case when both of those things are even. And so again, it's understood there's a 2 there. Even though the 2 is not there, the 2 is there. It's understood when there's a square root, it's going to be a 2 there. When those are both even and they match, you must put, really when they're both even and you match, you must put absolute value bars. So I could, if I wanted to, I guess, say, well, this is really the absolute value of 7, which of course simplifies to be 7. So I don't have to show that step. But on a harder problem, you will kind of need to use that step. So with numbers, it kind of works out. Like most students will get the answer of 7 given this problem almost every time. Okay, so here's where the rubber hits the road with this one. So if you have a problem like the absolute value of x squared, let's say it this way. Let's say the square root of x squared. So that seems a pretty simple problem, right? You say, well, the square root and the power kind of undo each other, so it's just going to be x. A lot of students will say x there, and they'll get the problem wrong. Because this is even, we have to use the property here and say the absolute value of x. And that's important on this problem because we don't know what x is. X could be -5, x could be -7, it could be a negative number. So if it's negative, like this one, it's going to come out positive. So when using numbers, it kind of automatically happens. When you're using variables, you have to remember to put the absolute value of x, absolute value whatever the variable is there. If that's even and that's even, taking the square root, the root, and the power even, then you do that. Okay, let's try a few. And let's simplify accordingly here. So there's some simplification we can do with this problem. It's kind of weird, but if you think about it, we can break this up. So we're going to use that first property. We're going to use this property to break up that thing there. So I'm looking for, whenever you see a third root there, I'm really looking for 3 of something. Well, I have 5 x's, so I could regroup this. I could say, well, that's really x to the third times the cube root of x squared. That's just applying that property. Because I really like this one because it's a perfect cube, and I'm taking the cube root of a perfect cube. So that's going to simplify, right? That guy's going to look a lot like just plain old x in a second. And this one doesn't simplify. It's just left as the cube root of x squared. So that's the simplified form of this, because it had a perfect cube in there. You've probably done this before. Like you've done this with, let's just go back to something you've had experience with. You've probably simplified square root of 20 before, something like that. And what I mean by that is, if you take the prime factorization of 20, 2 and 10, 2 and 5, you may know something interesting. We have a pair of 2's and a 5. So the fact that we have a pair of, so if I broke this up using the prime factorization, I could say the square root of 2 squared times the square root of 5. It's really the same thing, right? So this simplifies perfectly, 2 root 5. And I don't have to put absolute values on 2 because absolute value of 2 is positive 2, which is what that is. And you've probably done that before. So this is similar to that. It's just we're all with variables. Again, algebra 2, we're going to step it up from algebra 1. Now we're looking at cube roots. So again, this is stepped up. Well, let's look at this one. This one's a little easier, right? So let's do that 18 off to the side here. So 18 prime factorization would be 2 and 9, and then 3 and 3. So I could rewrite this as the square root of 3 squared times the square root of, let's see, 2 is still left over there. So there's a 2 and then 2 3's. And then x to the fourth, I might break that up. Instead of x to the fourth, I'm looking for pairs. I'm looking for, so whenever you see the root is 2 out here, because it's understood to be 2 for square roots, then I can think, well, that's really x squared here. It's really x squared. And then y squared, I'm just breaking them out. I don't think after a while you don't show all this work every single time here. But when you're first starting out, it's not a bad idea to show all that work. Okay, so now let's simplify everything here. So this 3 is now, it comes out, it's on the outside. The 2 is still left over inside of the radical. So I'm going to have the 2 inside of there. This is simplified. It comes out and it looks like absolute value of x. And this is absolute value of x. So times the absolute value of x times the absolute value of y. So that can simplify even further, I believe. So let's think about this guy for a second. And we talked about this property yesterday in class. When you have the absolute value of x squared, it's kind of redundant. It's kind of silly to say, well, x is positive, and then we're going to square it, and that's going to make it positive. What I could just say is, let's just call it what it is, 3x squared. That's still a positive number. It's kind of redundant to use the absolute value bars because there's 2 of them. I know that number is positive. Now, we need it for the y. So that's the kind of little picky thing that we do in math. So it's absolute value of y times the square root of 2. And that is a simplified form of the original question there. Here now we're looking for, whenever you see a 3 out here, we're looking for 3 of something. So off to the side, you might need to do kind of prime factorization of 54. So if we do 54, that would be 3 and, let's see, the 4 there. So 3 goes into, let's see, 3 times 9, no, 3 times, that's 30 and 24, so 18, I believe. It took me a while there. 3 times 6 is 18, and then 2 times 3. So I have a 3, a 3, and a 3. I have 3 3s and 1 2 left over here. So I'm going to break this up. I'm going to say the cube root of 3 to the 3rd times the cube root of 2, because there's still a 2 left over there. And I have 4 x's, but I'm really looking for groups of 3. So I might say the cube root of x to the 3rd times the cube root of plain old x. And then finally the cube root of y to the 3rd. That one works out nicely. It's going to simplify nicely. So this will be 3. I need to get that. It's still in the radical. I'll do that last. X times y. So that would be x squared times y times the cube root, the 3rd root of 2. Don't forget that, put that little cube there in the index, a little tiny 3 in there. And that's as simple as it gets. Again, I don't have to do absolute value because these are odd. So whenever that's odd, you just take whatever the a value is there. So we can combine some like terms with radicals. Like in this one, this would be 6 root 5. So it's kind of like saying 2x plus 3x. As long as the base, as long as the radicand, it's called, inside of there matches and the root matches, then we can add those like terms. So it works out really nicely there. Here it doesn't look like it's going to work, but I bet we can make it work. If we try to simplify 32, so do 32, 2, 16. If you keep doing that, it ends up being 2 to the 5th here. And then 50, now let's do the prime factorization of that. That's 2 and 25. Oh, I see what that is. That's really equal to 2 times 5 squared. So if we simplify this just a little bit, we can see that we have this 50 can be rewritten as 5 root 2. And this is really 16, square root of 16, which is 4, so that would be 4 root 2. So that adds up to be 9 root 2. So even though they didn't look alike at first, if you simplify them first, you may be able to add those non-like terms and get that kind of thing to work. That's the end of the screencast.